for thermodynamic. We start for thermodynamics last session, and today we're just going to finalize this part, the remaining information related for thermodynamics. We have here some information theoretical, and also we have many ideas for numerical. So first we start by ideal gas. Actually, we apply for ideal gas for last session, but today we will see some information related between the equation of PV equal nRT and the other equation PV equal mRT. So the general gas equation, it is PV equal nRT. B is pressure, V is volume, T is temperature, R is universal gas constant, N is number of moles. So for the equation have number of moles, the R used is 1 R for any type of gas. One value R is accepted to apply it for any type of gas. Okay, this general one. But for the other one, BV equal mRT, the other one here, BV equal mRT. BV and T here, the same BV and T. The difference only between NR here and MR here. N is number of moles, R is gas constant, this one is universal, R bar. But this M is mass per kilogram, and this R is a specific gas constant. Specific, it means this value according to the type of gas. So check the type of the gas, we can check the R value. But R here is one value accepted for any type of the gas. Okay, this R. This table here puts the values for R dash, universal gas constant. So, but you see here different values. Depend on what these different values. This is not different values. This one value but different units. One value but different units. Again, this one value but different units. Actually, this one is important. And we have another one is important. This we will use here for one example. But one of the important R bar I will give to you, but we will see in the problem itself. Maybe exam 4, we have equation used R universal, but in British units. So when we see this problem, I give you the value used for R bar for British as a unit. British is equivalent for this value, but in British unit. Equivalent for this, but British unit. Okay, back to the equations here. BV equal nRT and BV equal mRT. How to going to change it from nR bar to mR? Actually have a relation between number of moles and the mass. What is this relation? Is molar mass. What is this molar mass? M. M capital molar mass is also this value. It depends on the type of the gas. Okay, each gas have a different values for this M. According to this M, we can, and we know the number of moles, we can calculate mass. So if you're going to change from PV equal nRT to PV equal mRT, we're going to get M, which is equal to M capital multiply M. When you're going for the original equation here, BV equal nRT, so it will be BV equal N is equal M capital M small R bar T. Correct or no? No. Just back. Again. Yes. BV equal N is equal what? N here is equal M small by M capital. So I write it M small by M capital R bar T. This R bar divided by M capital, this one I take it and get another one is R, BV equal M R T. So this R, gas constant for a specific gas, is coming from where? Is coming from R equal R bar by M. It means it's coming from universal gas constant divided by molar mass for each gas used. Okay, now we know this R coming from where? R bar by M, like this. Okay, what else here is important? This equation. I can write this, maybe this better. Rho, better than D. What is rho? Rho is density. What is density coming here? Why? BV equal MRT, correct? Yes. So we know the definition of density is mass by volume. So if we're going to get mass by volume in one side, so what is remaining? It will be going this V here. So I will take it this in another way, is equal B over RT. So what is M over V? Is density, which is equal B over RT. So we have another relation, density, coming from this equation. Okay, this density for the gas is equal B over RT. Why I write it all this information? We have one problem in exam 4. The idea to solve one trick inside these steps, how to get density for this, and given B and T and the R is a constant. So if you know the B and T and the R and this gas, you can get density to use it in another equation. Okay, we'll see in this in details how to solve it, but the idea how to get density from this relation, rho equal B over RT. If it is not easy to save it, it's better B equal rho RT is the same. It means I just put the V in other side here, M over V, and keep it the equation as it is. B equal rho RT, rho RT, that's it. Which is better for you to save it, it's okay. Rho equal B over RT or B equal rho RT, that's it. Both the same. So from this slide, we'll see BV equal NR bar T. R bar here is one value for all gases, is a constant for gas. And the other equation BV equal MRT, and this one used for specific gas. And the last relation is B equal rho RT. Okay. The expression for sensitivity of pressure thermometer, change in pressure per unit change in temperature of ideal gas equal. Just to check here the definition of this sensitivity. If we're going to check this one, we can select the right answer easily. Anyone can get answer? What's the definition here? Change in pressure per unit change in temperature. Pressure per unit change in temperature. So just first write the equation B, V equal N R bar T. So what you want? B over T. So B over T equal N R bar over V. That's it. This in this side, this in this side. Finished. Any question? Clear? Clear? So
Yeah.
the answer correct is D. Let's see this example here. 0.12 gram sample of CH4 gas occupies a volume of 200 milliliter at 35 degrees C. What is the pressure of the gas in millimeter mercury? So the given here is mass. 0.12 gram, volume 200 milliliter, which is equal or equivalent 0.2 liter. temperature 35, which is equivalent to or equal to plus 273. So it will be 803 Kelvin. And the R, what is this R? This R bar, one value for all gases. So this value here, constant. He used this liter atmospheric per mole Kelvin to be matched with the volume unit liter to be matched with the other units. That's it. So let's see what is the equation would be used. The equation here to get the pressure, we have one equation, BV equal NR bar T. So what is the required? The pressure, what you have, volume we have, R bar T. So what's remaining? N. But you give you small things just to guide you to get N. What is this? Is a mass. How to get N from the mass? We have a relation between N and M. What is this relation? Molar mass. Molar mass is equal what? M over N. So number of moles is equal M, sorry, M over M. Actually, M we have, which is 0.12 gram. What is M? It's not given, but just if you check the type of the gas, we can check. This one, we know the carbon is 12. We know the hydrogen is 1. So CH4 means 1 from the carbon, 12, plus we have 4 from hydrogen, 4. So the molar mass for this is 16. So just M, this one is 16. So we have now N. Every parameters here, B and N and R and T, we have T is must be Kelvin. Volume, we write it as a liter as it is, because here I bring the value for the R with the unit of liter, so it's accepted. But check here, what you get the pressure here, the unit is atmospheric. So the pressure at the end, you get it by atmospheric, but the request here pressure by millimeter mercury. So once you get the pressure by atmospheric, change it to millimeter mercury. How to going to change this from atmospheric to millimeter mercury? It's not in converter, but it's easy conversion. 1 atmospheric, as we know, is equal to 760 millimeter mercury. This is a conversion, famous. Once you get the value by atmospheric, you can change it by this conversion. Let's see the answer here. Here, first one is get the number of moles. Okay, this value divided by 16, 16.04, this exact value. But if you don't given this value, so I can get the value exact, I just write it as it is, just make calculation for this. So this is a value for number of moles. Temperature, we change it. Volume, we change it to be standard. So we can get pressure directly from this equation, B equal NR bar T over volume, like this. You get it at the end, the value by atmospheric. How to change it from atmospheric to millimeter mercury? Just like cross multiplication. 1 atmospheric, 760 millimeter mercury. So 0.9459 atmospheric. What is this value? Cross multiplication. This one way. Other way, as I did it in many applications for numerical, this atmospheric. So I needed to change from atmospheric to millimeter mercury. So write it below the same unit here, atmospheric in numerator, put it in denominator, and the other unit you want above. So 1 here, atmospheric equals 760 millimeter mercury, and you check, you're going to multiply, you're going to divide, as we see here the conversion factor. This two way for conversion, this first way and this second way. Okay, you get the same answer. Any question? Everything clear? Okay.
Yeah, it's clear.
If you check this problem, you found different parameter change it. It is not two parameter change with the third one is constant. No, we have a pressure and volume and temperature. The three is going to be changed. So in this case, normally we consider number of moles is the same. So we write it as we know, BV equal nRT. If you consider N and R is constant, so BV over T is constant. So it means B1 V1 over T1 equal B2 V2 over T2. This we applied in the case of a change for the three parameter B and V and T. Okay, so here as this per equation you read it, you found the three is changed. For example, here this is the first volume V1, and going to the temperature here, this T1 and this P1. So this is totally first case. What will be the volume? So the request here is V2, and when the altitude where the temperature is blah blah, this T2, and the pressure here is B2. So it's given B1, V1, and T1. So first case is totally given. And second case, we have a B2 and T2, but request V2. So we apply for this equation. Okay. Be careful, please. For the pressure, we don't have any problem to use it, say, units the same without any going to change from this unit to another standard unit like millimeter mercury and millimeter mercury. We don't need to change it to atmospheric. We don't need to change it to Pascal or something like this, because any change for the unit of the pressure is by multiply. So if you're going to multiply right and left, it's cancelled together. But temperature is a must, because the temperature changes from Celsius to Kelvin, and going to change from Celsius to Kelvin by plus. This one is plus 273, this one is plus 273. So in this case, we can cancel 273 from these two sides. So it is a must to change from Celsius to Kelvin. Pressure, no problem. Just keep it in the same units, but it's no problem to change into standard. Okay. Volume as it is, no problem, the same. This V1 is liter, so we can get V2 by liter, no problem also. So here we're going to apply for the problem here, direct substitution. B1 is 757.2 multiply 6.25 liter millimeter mercury, 28.5 plus 273 equal, here is 366.4 millimeter mercury multiply V2, it is required, minus 34.35 plus 273. That's it. Any question?
No, it's clear.
Characteristic gas constant is R, and we already talk about for R a lot, so we don't need to talk again for this one. Just R bar here is a value for general. This for specific, for example, but for specific, which gas? If we said specific, which gas? This for air, for example. Why you write it air? Because this is a important one coming a lot. Almost many application or many problems for numerical coming for air. So it is better to save this value of this. R equal to 87 joule per kilogram Kelvin. Also this CB 1 kilojoule per kilogram Kelvin. CV this 0.718, and the K, or sometimes we can say this gamma is 1.4. Gamma actually it is CB over CV, and R is actually CB minus CV. This is the original equation coming from it. Okay. Specific heat of air at constant pressure is equal to specific heat of air at constant pressure. It means specific heat is C. At constant pressure, it means CP. So what is the correct answer? CP for air.
1.
0.21.
All this value for air. Just I remind you, this value, this value, this value, this value, all for air. Specific heat here, CP is specific heat at constant pressure, CV is specific heat at constant volume. Let's see some question for this one. First question, why is a specific heat at constant pressure greater than specific heat at constant volume? Actually, specific heat for constant pressure is considered the flow movement, the expansion for the flow itself, BV or B delta V. So the specific heat for CB is greater than the specific heat at constant volume CV, because the heat is added at constant pressure and the substance expands and work. You can obtain work. Okay, B delta V. What's meaning or definition of a specific heat, whatever at constant pressure, at constant volume? This is general definition for both. Specific heat, it is the amount of heat added to increase the 1 unit of mass 1 degree C. The amount of heat added to increase 1 unit of mass 1 degree C. Okay. Here mention 1 degree Kelvin, both the same. Just 1 degree is C, K, Celsius or Kelvin, the same. Another thing, we have two values for specific heats in gases, but we only have one specific heat for solids and liquids. Why? Actually, for if you remember pressure and the volume relation, we have a relation between pressure and the volume in case of gases, because when you're going to change the pressure, the volume will change. So this compressible flow. This in case of gas. But for liquid and solid, when you're going to change pressure, the volume is not a change. So in this case, there is no effect for the volume. With effect over the pressure, we only have one specific heat. But in gases, we have two specific heats. One at constant pressure and one at constant volume. These some values for ice, for water, and so on, water vapor. But just I make this bold because this is the important one. Equation for example, you remember, I think we saw, I will solve with you this one. I already solved with equation last session, last problem. Q equal Q lost equal mc delta t. You remember this one? This C, if the problem is talk about for water, so this C is 4.187, or you can check it 4.2 easier, 4.2. Okay, kilojoule per kilogram Kelvin for water. Okay, it's coming in the exam a lot to apply for this equation. The behavior of gases can be fully determined by, sorry, the behavior of gases can be fully determined by, and you have a problem for, no, no one have a problem. Anyone got answer?
3 laws. C.
Three laws is which is Boyle's, Gilasic, and Charles, but actually we have another one, which is we studied last session, Avogadro's hypothesis. Okay, and this relation between number of moles and volume. So is 4 laws. Ratio of two specific heats of air is equal to, just ratio between two specific heat, it means CB over CV. What is referred to CB over CV? Refer to what? CB over CV.
Undivided.
CB over CV. Refer to what? I tell you. I give you two definition. I write it here. We have two definitions, CB minus CV, CB by CV. This one is R, and this one is gamma or K. Okay, so what is the answer here?
CP over CV.
Yes, so the answer is 1.4.
So it will be
1.4 is the correct answer for gamma or K. 1.4 for air. Boyle's law, PV equal constant, is applicable to gases under
B.
yes, actually is applicable for small ranges of pressure. Joule's law. Joule's law actually said internal energy of ideal gas is a function of absolute temperature only. Okay, this definition is coming as a theoretical question in the exam. Internal energy of ideal gas is a function of absolute temperature only. So for any calculation related for internal energy is a function of temperature only. And also, according to that, we have enthalpy is equal to U plus BV. This enthalpy. We solved the last equation last session, applied for this. Specific enthalpy equals specific internal energy plus pressure, specific volume. So this function of temperature only, and if you're going to check BV applied by substituted by ideal gas equation, BV equal nRT. So BV is equal what? nRT. nRT. So if you consider number of moles constant, and by default is R is constant, so this constant. So it means this term is function for what? Temperature, and this one function for what? Temperature. So also enthalpy is default by default is function of temperature only, same like internal energy. So internal energy is function for temperature only, and also enthalpy is function for temperature only. Clear?
Yeah.
Just a minute, please. So now internal energy and enthalpy both is function for temperature only. We have theoretical equation for this one, and the numerical we already apply for this equation last session. This one. Which law states that the internal energy of a gas is a function of temperature only?
B.
Joule's law.
Joule's law, yes. Same volume of all gases would represent their
Specific gravities.
molecular weight. Molecular weight. Open system is
Both energy and mass cross the boundaries of the system. B.
C. Exactly.
C.
Okay, C, C. Yes, exactly. According to which law? We have some words in the question just to give you the correct answer, just to guide you.
Boyle's law?
Actually, he mentioned at the end, pressure remains constant.
Constant. Yeah.
So-
temperature is varying here, so it is not a just
Charles,
so
pressure constant. Gases have
two values of
two values, Cp and Cv. According to Avogadro's hypothesis,
B.
not B, it's totally far. The exact
A.
answer is molecular weight of all perfect gas occupies the same volume under same condition of pressure and temperature. B and T is constant. This is a condition for Avogadro's hypothesis. Sorry. Work done in a free expansion process is work done in free expansion process is
0.
0. Statement that molecular weight of a gases occupies the same volume.
For the previous question, I just want to know this. It's 0. I just put a guess actually, but what is the reason behind that? It's because of free expansion. It is
Yes,
like that, or
there is no work here. Free expansion,
okay.
no effect for force.
Okay, thank you.
You're welcome. Is this the same question? Maybe not the last one, the previous one. If you just remember, but I change. Question is now is the answer, and the answer is the question, and so on. Read carefully, you get the answer. You don't get answer?
Dalton's law.
No. You are selecting
Avogadro's.
if you use the engineers, select this one here for question answer the number B.
Avogadro's.
Yeah.
Avogadro's.
Avogadro's hypothesis. To convert volumetric analysis to gravimetric analysis, the relative volume of each constituent of the flue gases is volumetric analysis. It makes analysis for the gas by volume, like the total we consider all as at 100% volume as a volume, and just define the concentration for each one as a percentage of volume. But gravimetric analysis is defined by mass, not considered by volume only. No, defined as a mass. Okay. So, what is the relation between these two? How to get from one to another, convert it from one to another? Anyone knows the answer?
A.
Actually, it is multiply by molecular weight, not divide, multiply. If gas is heated against the pressure, keeping the volume constant, work done will be if you remember what I said to you in the first session, I think so, or second maximum, I think first, about pressure, you can remember his answer.
Gas is heated against the pressure.
It's
The work
A
should be zero
positive.
actually.
0, 0.
Yes, zero. This
Zero.
definition. Remember the first session terms and the definition of work. If you
It's
remember,
A.
Yes.
zero because volume constant. Isolated system means
Neither mass or energy cross the
Exactly.
boundaries of the system.
yes, exactly. Properties of substance like pressure, temperature, density, thermodynamic coordinates are what is this? Path, point,
Path functions.
real.
Pressure, temperature, and density.
Point functions.
Point function, exactly.
Point functions.
Which of the following quantities is not the property of the system? Which of the following quantities is not the property of the system?
Heat.
It's a density.
Pressure, temperature, performance.
Not quantity.
Space,
Not property. Which one is not property?
specific volume.
Actually, specific volume is a property. The only one it is not a property is heat.
Heat.
Heat is a path function. According to Avogadro's law for pressure and temperature, each molecule of a gas is, as per definition, each molecule of a gas occupies same volume. Homogeneous and heterogeneous system. What's the difference between these two? Homogeneous system, it is a system which consists of a single phase. Like we're going to add different items together, but at the end, this mixture, it will be one phase. But heterogeneous system is a system which have more than one phase, like two phase or more. Two phase or more. Like for example, this here just defined between sand and water, ice and water, two different clear two phases. Okay, so this is heterogeneous. Mixture of ice and water form a
There are ice and water. Or what?
Heterogeneous. D.
heterogeneous system. Yes, exactly. Which of the following is the property of a system? Property.
All of above.
Yes, exactly. All these properties. All this. Weight basis. The air contains how many parts of oxygen? Weight basis. What mean of weight basis? It's like by gravimetric analysis, because we have another percentage according to volume basis, but here ask for weight basis.
21 or 23?
23.
23 for weight basis, 21 by volume basis. Which of the following is not intensive property? Not intensive.
Heat.
Exactly, heat. Let's focus with me, please. First law of thermodynamics and second law of thermodynamics and third law of thermodynamics. Actually, zeroth law of thermodynamics we studied last session, which is mean two bodies in thermal equilibrium are the same T temperature. Okay. First law of thermodynamics. Define here first law of thermodynamics. First law of thermodynamics as energy can never be created or destroyed. Energy can never be created or destroyed. Going to change it from shape to another, but never to be created or destroyed. But going to change it from phase to another or shape to another. So the equation for this one is famous equation, used a lot, coming a lot. What is this equation? Delta E, the change of internal energy, is equal to Q plus work. Okay, we have this sign is minus for some textbook or some searching on internet, but actually it's not important to me to be aware positive, negative, no problem for me, because at the end Q it can classify positive or negative according to it is into the system or out of the system. Also work it can define and write it here and describe and substitute it here for the equation positive or negative according to into the system or out of the system. So it's not important for me the sign. Okay, it's important during substitution itself. Clear? So the change of internal energy is equal Q plus work, heat plus work. The second law of thermodynamics. This second law of thermodynamics coming to can classify the system. First, to can measure the entropy of the system, and also second thing to classify this system is applicable or not. It means first law of thermodynamics, we can substitute it and apply for any system, whatever this system, it can happen or not happen. Okay, if it is possible or not possible. It means there is not defined this possible application or not. Yes, it can't define that. Why? For example, if you have a cup of tea, for example, cup of tea. This cup of tea have a tea here is hot, correct? And the surrounding here. So the surrounding here, the temperature for the surrounding is 25 degrees C, for example. And the tea here is at least 50 degrees C or 60 degrees C, at least. So if I'm going to just study the system here as a T, this is the system for me to study. What do you expect? The heat is going from where? The heat, it should be going from the cup of tea into the surroundings. So the heat is going out, correct? Yes. But actually, if I tell you, no, heat is going from the surround to the cup of tea, it means it's impossible. It can't happen like this. It can't happen. Impossible. Heat's going from hot to cold. No, I applied from cold to hot. So if you have amount of the Q here, for example, is X, but you're going to substitute as a negative X, when you expect this one is going in. For both cases, for case 1 and case 2, we can apply first law of thermodynamics, no problem, and you can get answer. Change of internal energy is equal Q plus work in first case and second case, and we can apply it for 2 cases and you get answer and so on. Okay, but can't define this system is applicable or not. So how to can use it or define the system is applicable or not? By second law of thermodynamics. Second law of thermodynamics is measure something is called entropy. Entropy, actually, it's not easy to define. Entropy is just going to define something related for the random or disorder of the system. Okay, the random of the system or disorder. Just imagine with me. Any system, in the first case, when this case is changed to second case, what happened? We have something additional, work, heat, temperature increase, whatever, something happened, correct? This happened with an ideal process or real process. Normally for real process, we have some random happen during the process. It's not ideal. So this random is defined or can described in the form of entropy. Okay. So if you're going from state 1 to state 2, we have an energy change due to entropy happen here. Whatever heat and work happen, but also entropy. Okay. For example, flow go through in the throttling like or porous plate like holes, and the flow coming with high pressure. And after this porous plate is nothing, its pressure is down. What happened? Entropy increase when you go into this porous plate. Something happened here, entropy increase. We have two gases, we have a diaphragm between these two gases, and you remove the diaphragm. What happened for these two gases? It's going to mix together. What happened due to what? Entropy, disorder, random. Okay. So if you go back for these two gases after we remove the diaphragm and mix it together, when I back the diaphragm again, the gases, it will be separate again? It can't happen. According to what? Entropy. According to entropy. This seems like this concept. It can't happen. The temperature from around 25 is going to inside for the cup of tea is 50. This can't happen. How to define this by equation? This equation, we can use it. For this equation here, he said the change of entropy of the system, of the total, the change of entropy total is equal to the change of the entropy of the system plus the change of entropy in the surrounding. It means I'm going to calculate the entropy for the system alone. How to calculate S Q by T. And going to calculate entropy for the surrounding. How to calculate Q by T. But Q here is the same value but different sign. So if you're going to calculate for the case of this out of the system, we define this as a positive, this negative. But here into the system, this one, it will be positive, this negative, according to the direction for each one. So here, this I will calculate for surrounding, this for system, calculate S here and there. Okay. For first case, cup of tea going out for the Q to the surrounding, we will found this value, entropy system plus entropy surrounding is more than 0, is a positive value. So it's applicable to happen. But when we're going to change the direction here, this sign will be changed, this sign will be changed. So we're going to calculate system, entropy system plus entropy surrounding. We'll found this one is less than 0. So if this one is less than 0, it means this is impossible process. Impossible process. Is clear? Last law here, he said when the entropy of a pure or perfectly crystalline compound, so this at T equals 0 Kelvin. What happened at 0 Kelvin? 0 absolute pressure. What happened? This entropy is equal to 0. Perfect. This entropy is equal to 0. Okay. Focus for second and first law of thermodynamics, please. Which of the following substances, internal energy and enthalpy, are the function of temperature only?
Perfect guess.
Perfect guess. Okay. free expansion process.
Work done is 0.
Yeah, we agree with you. Work done is 0. But actually also heat transfer is 0. So answer is NB. Throttling, this is a throttling process. The throttling process is actually the flow is go through the porous plate. It is very narrow hollow. So high pressure flow coming, this is coming from here, from this narrow. What happened? Pressure is going to decrease down. Okay. And is going to be something is uniform some sizes. Okay. This passing through porous plate. So it is high entropy happens this. Entropy increase, entropy increase. So throttling process here is a flow is passing through narrow holes from the porous plate. Okay, this process here has some notes here, but we're going to define this in details for next slides. Entropy actually increase. Process is not isentropic. What's mean by isentropic? You'll check this later. Isentropic, it means adiabatic and reversible. So this process is actually adiabatic and not reversible. What meaning of adiabatic? Adiabatic, it means no heat transfer. And please be careful because he play with this in the exam. You will have a difference between no heat transfer and temperature constant, T1 equal T2. We have two different cases, two different process. No heat transfer, it means adiabatic. Constant temperature, it means isothermal. Two different, okay? A reversible, it means the state 2 come back to state 1 again, to original state. But actually this process for throttling after passing the narrow is going, if you're going back, the pressure increase direct, it's impossible to happen. So it's not reversible. For isentropic process, it means combined between adiabatic and reversible. Actually it's adiabatic this process, but not reversible. So totally it is not isentropic. But what's mean or defined by isentropic also? Isentropic, it means delta S equals 0. Entropy constant. Entropy what? Constant. It means entropy for state 1 is the same entropy for state 2. There is no change in entropy. Actually, it not happen. Entropy increase. So delta is not equal to 0. So it is not isentropic. Okay. If gas vapor is allowed to expand through a very minute temperature, then such a process is known as
Adiabatic.
no.
Expand to a very minor temperature.
Throttling process.
Throttling.
Just combine all process in one slide. What is the process here we're going to study? Isothermal, isobaric, isochoric, adiabatic, and also what's mean of reversible, irreversible. Isentropic already we studied. Reversible can happen slowly in either directions. This direction come back to the original. Irreversible, it can't back to the original. And it means by default entropy increase. Entropy increase. As you see here, can't go backwards. Let's see the other processes. Isothermal. Isothermal, it means constant temperature. So constant temperature, when you're going to apply for first law of thermodynamics, first law, it means delta E. Delta E, it means delta U. Change of internal energy equal Q plus work. So when temperature constant, so this is change, this is a function of temperature only. Temperature here is 0. So it means Q is equal work. Q equal work. Isovolumetric or isochoric, it means constant volume, constant volume. So for constant volume, work is 0. No change in volume, work is 0. So the internal energy is equal to Q. Let's see here in the figures. This isochoric here process, this, where is this? No, this one. This isochoric process, BV, constant volume here, you see this constant volume, isochoric or isovolumetric, and sometimes isometric direct. Okay, isometric, isovolumetric, isochoric, all the same, volume constant. There is no work here. Isothermal, this is the last one, constant temperature, constant temperature. So in this case, work is equal heat. Work is equal heat. Isobaric. Isobaric, it means constant pressure. Constant pressure. So at constant pressure, it means delta U is equal Q minus the definition of work, which is equal P delta V. And this is a process for isobaric here, constant pressure, PV diagram, constant pressure. Last one here, adiabatic. Adiabatic, no heat transfer. No heat transfer. You can say it here, no heat transfer. So for no heat transfer, Q equals 0. So the change of internal energy is equal work. This one is adiabatic. And isentropic, already we discussed this last slide, isentropic, which is mean delta is equal constant. Here also we can make a summary. Here, this is summary for all process. This one is constant pressure, isobaric. This one is number 3, constant volume, isochoric or isometric. This one is isothermal, and this one is adiabatic. Clear?
Yeah. Clear.
Okay. Specific heat of air increases with increase in
Temperature.
Both pressure.
Both pressure and temperature.
temperature only.
Temperature only.
Fluid expands suddenly into a vacuum through an orifice of large dimension. Then such a process is called
Throttling. E.
tricky question.
It says into vacuum.
No, free expansion.
S-
Which of the following processes are thermodynamically reversible?
E.
C.
Yes, isothermal and adiabatic. Which process is irreversible?
Throttling.
Yes, sure.
Okay.
In order the cycle be reversible, following must be satisfied. To be easy for you, all these cases is a reversible cases. Okay, all this cycle is reversible cycles. Clear?
All the above.
All of them. Thermodynamic process to be reversible, the temperature difference between hot body and working substance should be to be reversible.
Maximum.
Just check. Wait. Reversible. Reversible. Come back to the original state. 0. This is a good question. Minimum work in compressor is possible when the value of adiabatic index n is equal to, you know by adiabatic index? Actually, the equation for calculation of pressure is V equal constant. The general one is V to power N equal constant. What is this in? Adiabatic index. Okay. When we can obtain minimum work. This one used for calculation of work. So when this can be minimum.
When it will be 1.
Exactly. When this N equal to be 1. When equal to be 1. If N equal to 1, so BV equal constant. This isothermal process. And another one is BV equal to gamma, which is adiabatic. And in between BV equal N equal constant, this polytropic, normal one, as N independent of N. This minimum work, this maximum work, this in between. Clear? So minimum is 1, maximum is 1.4. Molecular volume of any perfect gas at 600 times 10 to the power 3 Newton per meter square at 27 Celsius will be, molecular volume is just like something like volume per mole, is something like this. So if you expected this, BV equal nRT. So if you need V divided by N, so it's something like RT divided by P, which is equal, R is equal 8314 multiply temperature 27 plus 273 divided by 600 multiplied 10 to the power 3. So the correct answer is 4.16. So answer is what? A. This from where? This R bar, general gas constant, 8314. Okay. This famous value, if you just remember, 8314 by standard units. A gas is compressed in a cylinder by a movable piston to a volume 1/2 its original volume. During the process, 300 kilojoule heat left. The gas and the internal energy remain the same. The work done on gas in Newton meter will be. This is a long question, but just in small words, he give you answer like this. Read in 30 seconds and just